Okay, so let's continue with the weak and strong forms. Now, let's see how we can obtain the weak forms and strong forms in physical problems. So heat transfer problem, one-dimensional stress analysis, and diffusion problem. Now, of course, here gamma denotes the boundary of the object that we want to analyze. Let's say that this is our object, and at arbitrary locations we have different boundary conditions. Now here U is for displacement and T is for traction force, traction. So this basically means that we have some specified displacement at certain locations, and we have some external loads on certain part of the boundary. Now what it means, simple. Gamma T is for traction boundary. Let's show it with the blue color. Sorry. So this is the traction boundary, and gamma U is the displacement boundary in stress analysis. And the union of these two forms the overall boundary. In fact, for the definition of the problem, intersection of the traction boundary and the displacement boundary is zero. So they do not coincide, which means that there is you cannot define the displacement and the traction boundary on the same place. So this is what it means. Okay, so these are the definitions for the boundary conditions, and in fact we know we have the force equilibrium. In fact, E multiplied by du dx is the stress, and multiplied by A means that the force. So the change in force d dx in x direction plus external loads has to be equal to 0. Now we limit x from 0 to L. 0 is the lower bound and L is the upper bound of the domain that we are interested in. And here, of course, there is another thing. Omega defines the domain. Now let's look at the boundary conditions. The traction force, so which is defined by the sigma multiplied by the n. N is the outward normal here. So it is the outward normal vector, and that's equal to E multiplied by N du dx, and that's equal to the traction force on the stress boundary condition, and moreover U is equal to U bar on the gamma U. So we have T here and gamma U here. Now we can write the any function, but so remember that let's weight the derivative of a function f. So w df dx integrated in the domain omega. Here omega is the domain that we are interested in. Let me show it like that. So the domain is the omega. W df dx, integration over the omega. We can apply integration by parts to here, or Gauss divergence theorem. So that is Wfn gamma minus integration over the omega f dw dx. So this, from here, we can obtain Wfn gamma u. So we can decompose this boundary term into the boundary term where the displacements are prescribed, and boundary terms related with the domain boundary section where the traction forces are prescribed. So minus integration of f dw dx over the domain. Now there is one thing, again, here we said that n is the unit normal. N is always an outward vector. This is n. It's the outward unit vector, by the way. Okay, so we apply we can use the Gauss divergence theorem, or integration by parts, let's say, like this. Now, next step is applying this to the stress force equilibrium in one-dimensional structure. So remember that we take the weight of the force equilibrium in one dimension, d over dx. A is the area, E is the Young modulus, du dx here, again, plus B. U is the displacement, and this is valid in omega. Now, at the traction boundary, we can say that WA T bar minus sigma n is equal to 0 over the traction boundaries. And from there, we can easily say that WA sigma n gamma u, sigma is the stress at the prescribed displacement, plus WA T bar gamma T minus dW dx, integration of dW dx multiplied by the area multiplied by the Young modulus du dx, plus integration of W multiplied by B. B is the distributed force or external loads, let's say, over the omega, for all omega with W is equal to 0 on gamma u. So remember that this is the condition for the essential boundary conditions. So W is the weight. Now, here we define u of x on a function space U. So Ux is a member of Hilbert space with U is equal to U bar on gamma U, and this Hilbert space is a subspace of C0. So remember that C0 is the space of function where the values are continuous, but the derivatives may be discontinuous. Now we can define the weight function. So this is U is the trial solution here. U0 is the Wx. Wx is again a member of the Hilbert space. W is 0 on essential boundaries or Dirichlet boundaries, Dirichlet boundary condition. Okay, so from here, since W is 0 on gamma U, this term vanishes. And we don't have this term, and we are left with the stress traction boundary condition. Therefore, we can have the weak form as dw dx, integration of the dw dx multiplied by the area multiplied by the Young modulus du dx, and that's equal to WA multiplied by the traction at stress boundaries plus integration of the distributed loads in the domain for all value of the W, which is the member of the U0, which is defined previously. So U0 is the function space. Okay. Now this is the weak form for the one-dimensional stress analysis. If you solve this weak form, you will obtain the solution for a problem. Now, let's look at the heat conduction problem. So, similar to the stress analysis problem, we use the Fourier heat transfer law. Here, K is the conduction coefficient, A is the cross-sectional area, and S is the source term. So again, we have the domain, and this differential equation is valid in the domain omega. At the we have the flux boundary conditions, so Q multiplied by N. Again, N is the unit outward vector towards the domain, and that's equal to minus K multiplied by N dt dx, and that's equal to Q bar. So Q bar is the prescribed heat flux in the normal direction. Of course, we have the boundaries where the temperature is defined. So at these boundaries, temperature is equal to T bar. Let's obtain the weak form for heat conduction problem. Again, we begin by weighting the strong differential equation which represents the heat conduction in the domain. And then we apply integration by parts. Certainly, in the domain, this integral has to be equal to 0. Now, on the boundary where the flux is prescribed, this expression has to be satisfied. And furthermore, we have the prescribed temperature, and on the prescribed boundaries, weight function has to be equal to 0. Now, if we apply the integration by parts, again, we obtain this integral equation. It is integration of dw dx A multiplied by K dt dx over the domain omega, and that's equal to W multiplied by A multiplied by K dt dx multiplied by n over the boundaries plus the source term. Now, of course, again, since weight is 0 on the prescribed temperatures, on the boundaries where the temperature is prescribed, we can say that the weak form is then can be written as in this form. So this is the integral equation again. So it is the integration of dw dx a multiplied by k dt dx over the domain omega. On the right hand side, it is minus wa q bar over the boundary where the heat flux is given. Q bar is the incoming heat flux plus integration of W multiplied by S over the domain omega. Now this is the weak form for the one-dimensional heat conduction problem. Certainly you can use generalized boundary conditions. So how we can define the generalized boundary conditions? Now we want to implement the boundary conditions, and remember that after obtaining the after choosing the trial and weight function, so the weight function has to be 0 on the prescribed boundaries, on the Dirichlet boundaries. But how can we obtain the how can we prescribe the Dirichlet boundary conditions? There are different techniques. One way is the implementation of the boundary condition in a strong manner. In that case, remember that we choose a trial function which satisfies the Dirichlet boundary condition or prescribed value of the dependent variable. But sometimes we want to enforce the prescribed boundary condition in a weak sense. Therefore, we use generalized boundary conditions for such kind when we want to implement it in such a manner. So how we do it? Again, we have the differential equation which represents our physical problem. As you see in the heat conduction and stress analysis, they both have the same type. Here, theta is the dependent variable. There exists a constant k, and there is another constant a, which represents the area. Then the derivative of the dependent variable is equal to some value, and moreover, on some part of the boundary, the value itself is equal to some others. Here, gamma capital phi is the overall boundary of the domain. Furthermore, depending on the type of the problem, theta and other constants may change. So in elasticity, theta is U. In heat conduction, theta is temperature. And for diffusion problems, it is C. K, the constant K, the physical constant K is the Young modulus for elasticity, conduction coefficient for heat conduction, and diffusion coefficient for the diffusion problem. Here, F, the source term, is B in elasticity, which represents the distributed loads. It is S, which is the heat generation rate, and S, which is the source or rate of generation of particle at a certain location. Moreover, here we have phi bar. It is the traction, prescribed stress T bar. It is minus Q bar for heat conduction and minus Q bar rate of diffusion or diffusion at the prescribed boundary, and so on. So furthermore, here we have a new constant, beta. Now this beta is used for generalizing the boundaries, and it's a penalty parameter. So basically we penalize the boundary condition. Therefore, we can define the whole boundary as if it is Neumann type boundary condition. So as if it is, there exists some stress type or heat flux type boundary there, even though the displacement is prescribed there. Okay, so let's see how it works. Now let's obtain the general strong form, general weak form for the one-dimensional problems. Again, we have the differential equation which is represented, and then we have the generalized boundaries on the omega gamma. So we have this together forms the strong form. Of course, you can partition the boundary. In that case, we have one differential equation which is then, valid in the domain omega, and we have the flux boundary. There shouldn't be this term, this is 0. Okay, and we have the prescribed dependent variable on gamma theta. Okay, now again we begin by weighting the function on the domain. We use integration by parts, and as a result we obtain this integral equation. So it is dw dx a multiplied by k d theta dx. Here theta is the dependent variable, minus integration of wf over the domain omega, minus wa phi bar minus beta theta minus theta bar over the domain gamma for all value of the weight function, which is the member of the Hilbert space. Now, since in penalty method we don't have any essential boundary conditions, so w can be any function. So w it's not necessarily be w is 0 at some part of the boundary in this case. Of course, in the partition method it's a little bit different. So theta x is again a member of the function space U, but in this case this is 0. Again, this term shouldn't be here. Okay, it's a mistake. Just exclude this part. In the partition method, theta x has to be equal to u such that the w dx a multiplied by k the theta dx dx minus wf dx minus wa phi bar. Now w has to satisfy sorry, has to satisfy the u0 in this case. So remember that, so w has to be 0 remember that u0 in in function space u0, w has to be 0 on the prescribed boundary conditions, on the prescribed boundaries. Okay. Now, there is then another type of problem that we have, and that is advection diffusion problem. What is advection and diffusion? Now, remember that when we are talking about a diffusion, we have a glass of water. Imagine that you have a glass of water and you put a droplet inside a glass of water. So the water is still, water is not moving there. And eventually you see that at the beginning of the process, the ink is very concentrated and the color is very dark. So basically the number of the paint particles are constant and it's very intense. As the time proceeds, you see that that little droplet, the area that the droplet covers increases and the light is coming lighter. So the intensity in a unit volume decreases, but the total amount of paint particles are constant. Now this is what the diffusion is. How about the advection? Now we do it in a glass of water. What if you do the same thing in a river? In a river, the water is flowing and you just put a droplet of ink. For the moment, just imagine that there is no diffusion. Hypothetically, I'm just creating a hypothetical case. There is no diffusion. So you put the droplet inside the river and the particles cannot diffuse. So basically, these particles moves like a rigid body with the velocity of the river. So depending on the flow. So it will move in the direction of the flow. This is called advection. So basically the concentration make a translational motion with the velocity of the river. When the diffusion is combined with the advection, because we know that the particles will diffuse, so the both events happens together, both the advection and diffusion happens together in a river. So this is called advection diffusion. So how is the strong form of it? Again, so we have the theta. Let's say this is the concentration at a certain location. Here V is the velocity, A is the area. So number of particles that get into the system at location X with velocity V minus number of particles theta with velocity V at a certain area X plus delta X will give us the total amount of the concentration. So just think like this. You have a box. You have particles coming in and you have particles going out. And the number of particles coming in and the number of particles going out will, the difference between the numbers of particles coming in and number of particles going out will give us the amount of particles inside the box, inside the control volume. Now it is the same for the Q. Q is the flux of the particles and it is the derivative of the total number of the particles. And the difference in the flux will give us again the number of particles inside the box plus S, delta X multiplied by S. So this is the number of particles generated inside the box. And all of these has to be in equilibrium, and that has to be equal to 0. So as delta X goes to 0, we can obtain the differential equation which represents this problem. So this is the differential equation which represents this problem. d over dx, d over a velocity theta dx plus d over dx of area multiplied by the flux minus S will give us the flux. It has to be equal to 0, sorry. So the total equilibrium is due to the advection. So this is advective terms. And we have the diffusive terms. So this is why this equation is called advection diffusion equation. Certainly we have the prescribed again displacement and flux boundaries. Now if the incoming and outgoing areas and the velocities are equal, then dAV dx is equal to 0. There is no change. And from there, I can say that at a particular location, this term, if I take the derivative of this term, the second term vanishes because dAV dx is 0, and then I obtain this term, area multiplied by the velocity, as delta x is getting smaller and smaller, so the velocities will be coming very close because I'm just taking the limit. There is no sharp change in the velocity. Then I can easily write that I can neglect this term and I will be left with area multiplied by the velocity d theta dx. Okay, so this is the advection diffusion equation. Now from here I can write that the strong form of the advection diffusion equation as area multiplied by the velocity d theta dx plus derivative of the flux with respect to x, that's area multiplied by the flux, minus S. If I use the Fick's law, that is Q is equal to minus K d theta dx, and substitute this expression into this equation, then I obtain the, again, another form of the advection diffusion equation. Along with the boundary conditions, it forms the strong form. So I have the advective terms here, area multiplied by velocity d theta dx minus d over dx area multiplied by k d theta dx. K is the diffusion constant minus s, and this is valid in the domain. Theta is equal to theta bar on the prescribed boundaries, and minus k d theta dx multiplied by n is equal to q multiplied by n. That's equal to q bar on the flux boundaries. So now, after obtaining the strong form for advection diffusion equation, I can obtain the weak form for it. So what I do is, first I weight the differential equation, which represents the problem on the domain. Of course, I weight the flux boundary as well. Again, W is the weight function, and it is 0 on the prescribed boundaries. So I have, my first term is integration of WA V d theta dx over the domain omega. I apply the integration by parts to this second term after multiplying it with the weight. Then I obtain dw dx a multiplied by k d theta dx minus ws. Remember that s is the source term, integration of w multiplied by s over the domain. And then I have the flux boundary conditions, since w is 0 on the prescribed boundaries. So this is the weak form of the advection diffusion equation on the this is the weak form of the advection diffusion equation. So this is the weak form. Okay, so remember that the flux is then the type of generalized. So it has the particles carried by the velocity on the boundary, and change in the concentration as well. So I can put Q bar as so here I put the, instead of Q bar, I put this expression on the flux boundary. So I obtain the weak form. Again, W has to be 0 on the prescribed displacement. Now, there's another way of obtaining the weak form, and that's the minimum energy potential. And now, let's see. Solution of the strong form is the minimizer of the energy. So you basically want to minimize the potential energy of the object that you are interested in. So in case of a one-dimensional stress problem, it is the strain energy. So what is strain energy? Strain energy is the energy under the stress strain curve. So remember that if you have a linear elastic material, so let's say that these are my axes, and this is the vertical axis is stress, and the horizontal axis is strain. Now for a linear elastic material, your stress strain curve is linear, and the slope of this line gives you the Young modulus. So therefore the energy stored inside the material is basically the area under this curve. If you calculate the area under this curve, that gives you the strain energy, and that's equal to 0.5 multiplied by the stress multiplied by the strain. That's equal to strain energy. Okay, so simply you know that you can write it in two different ways. So you know that the stress is equal to strain multiplied by the Young modulus. This is one way of calculating it. If you substitute the strain, so epsilon multiplied by E, then you have 1/2 E epsilon square. And remember that epsilon is du dx. Then you arrive at this equation, this expression. This is the internal energy or strain energy in general. This is the energy stored inside a structure when you apply a stress on it, when you deform it. Okay, what else? Minus work done by the external forces. What are those external forces? Certainly the distributed load on the structure, B, and work done by the distributed load is U multiplied by B, because distributed load will deform the structure as well. And in fact, it is the deformation, the amount of deformation is the displacement U. What else? We have the work done by the traction forces. So you apply an external load, and then you calculate the work done by the external load. So basically, the potential energy is the energy stored inside the structure minus work done by the distributed load and work done by the traction forces. Now, if we minimize this potential energy, we will reach to the equilibrium state of the object that's deformed. And as a result, we obtain the solution of the strong form. Now, here we do something. We write the W, potential energy, for a given displacement. Okay? So we first calculate the W for a given displacement. Then we apply a very small change. Here W is some function, some arbitrary function. Okay, so we apply a very small change. So basically we have the displacement, and we give a small change into this displacement. And we look how the energy changes. So delta W is the change in potential energy or variation of the potential energy. And in fact, we have delta U. Delta U is some change in the weight function. Eta is here a very small value. So we give a very small perturbation. We make a displacement, we deform the structure, we store some energy, and then we give a very small change. And we see, we analyze how the potential energy changes during this small change. This is the objective now. So as a result, if you do the algebra, certainly the change in internal energy, delta or variation in the internal energy, is equal to du dx plus zeta dw dx, square of it, minus 1/2 area multiplied by the Young modulus du dx square. If we do the algebra, we arrive at this expression. So here we have area multiplied by the Young modulus du dx square plus 2 zeta du dx multiplied by dw dx plus zeta square dw dx square, and integration of this expression over the domain omega, minus 1/2 area multiplied by the Young modulus du dx square. Now here is the thing, since zeta is very small, this term is eta square is much smaller, because zeta is much smaller than 1. Let's say that it is 10 to the power minus 6, and square of it will give you 10 to the power minus 12. So it is negligible. Therefore, you can neglect this term, contribution of this term. And moreover, these two terms will cancel each other. As a result, we are left with just this term in the variation of the internal energy. So variation of the internal energy can be written as like this: zeta integration multiplied by integration of area multiplied by the Young modulus dw dx du dx dx. How about the external work done by the external loads? Remember that we give a small variation to the displacement, and as a result, the variation of the external loads due to the distributed load can be written as u plus zeta wb dx minus u multiplied by b dx. From here, you can easily obtain that it is zeta multiplied by integration of wb dx. W is an arbitrary function in the meantime, so we just choose an arbitrary variation in the displacement. And in fact, work done by the tractions is again identically calculated. So it is u multiplied by zeta multiplied by w, and that is multiplied by area multiplied by t bar. And if we subtract it from u multiplied by t bar, we arrive at this expression. So it is zeta multiplied by w a t bar. Now combining all these, work done by the external variation of the work done by the external loads can be written like in the expression So it is WB dx plus W area multiplied by T bar. Certainly, we want to minimize the potential energy. So the variation in the potential, we want basically the variation in the potential energy to be zero, even if we give a small perturbation to the displacement. So this is the equilibrium condition. From there, we can easily obtain the weak form for the potential energy. So that is area multiplied by Young modulus dw dx multiplied by du dx, and integration of this expression over the domain omega, minus w multiplied by b, integration of w multiplied b over the domain omega, minus wa T bar over the traction boundaries. Of course, again, Wx is the member of U0x, which means that Wx has to be 0 on the prescribed boundaries, or in other words, Dirichlet boundaries. Okay, so this is the minimum potential energy concept.